All right, and away we go with assignment 6H. 6H, I began by putting all of the theorems and all of the ideas that we need to be covering in this chapter. These are all quote unquote the fundamental theorem of calculus, like all of these things. And so we're going to be talking about some pretty important things like net change, the second fundamental theorem of calculus. This is that the average value that I was talking about before. So the average value, this was the last assignment right here that we were describing, and as well as just, in essence, the fundamental theorem of calculus means, in essence, if I take an integral of something, you evaluate it at b and then minus a. So that's that concept right there. This is the idea that we are running with right now. All right, so again, this is going to just be chock full of let's just take some integrals kind of idea, some definite integrals. So the idea behind taking a definite integral is we integrate, obviously. So this is going to be x squared divided by 2 is 3. I exclude any singular constants, and I'm evaluating this from 0 to 2. So this is going to be the evaluation of 2 minus the evaluation of 0. Pretty straightforward. All right, so here I take the derivative, so this is going to be x squared divided by 2 minus 1x. All right, so this is being evaluated from -1 to 0. So the evaluation is 0 minus the evaluation at 1. So that's going to be 1 plus 1. It's going to be -2. So here we go, t to the third, 1/3 minus 2t. Again, I don't take out like the 1/3 or whatever because, again, I have to take it out of everything if I do. And so I could turn it into a 6, I guess. All right, so 1, this is going to go into 1/3 x to the third minus 2x. Make it look like I didn't use a calculator. That's -5/3 minus the evaluation at -1. It's 5/3. This is -10/3. Okay, I'm going to rewrite this. I don't like denominators like that. So this is 3x to the -2 minus 1. So this is going to be x to the -1. That would produce a -3 minus 1x. From 1 to 2. So I evaluate that at 2. So this is going to be -3x to the -1, or I could have just wrote that as a division of x, minus x. So -7/2 minus the evaluation at 1. -4. So this is -7/2 minus -4, I guess. So that's 1/2. Okay. Here is a little bit tricky. Remember, we don't have any product rules or quotient rules. When I have an addition and subtraction in the numerator, I'm allowed to split this. So this is u divided by the square root of u minus 2 divided by the square root of u. And then, so u is to the negative 1/2, and this would be, well, an addition or AKA a subtraction. So this is u to the 1/2. This is like 1 minus 1/2. This is 1 minus 1/2. So it's positive 1/2. And this is just 2u to the negative 1/2, that side. So I'm splitting the numerator, and I'm kind of creating two separate numbers. You can separate numerators, you can't separate denominators. So this is u to the 1/2 minus 2u to the negative 1/2. All right, so integrating, this is u to the 3/2, 2/3. Let's go u to the 1/2. So this would be a multiply by 2, so the reciprocal of that, so that'd be -4. And this is being evaluated from 1 to 4. Without using the calculator, what do I think of to get these answers? So for instance, this is 2/3, and this is going to be 4 to the 3/2. All right, so what I think of is that denominator is a root, and that's usually what I try to do first. So I would square root, and that would turn it into a 2. And then 2 to the 3rd is an 8. So that's kind of what I would do. So this is going to be 8. So if you have to use your brain, this is what you do. So this is going to be what, 16/3 on that portion of the question. All right, so just we have the ability to use our brain if we absolutely need to. All right, but I'm going to use my calculator because that's a little bit quicker. So this is 2/3 x to the, and again, I want this to be, and so I have to put this in its parentheses as far as the calculator goes. 3/2. I could say 1.5. It doesn't really matter. Minus 4 to the, again, parentheses. Because otherwise it's going to recognize it as u1 divided by 2. That's what it's going to recognize it as if you don't use parentheses. I'm sorry, 4x to the 1 divided by 2. And that's what it would recognize it. So this is the evaluation at 4, -8/3. And then the evaluation at 1, -10/3. So this is -8/3 plus 10/3, 2/3. So this is t to the 1/3. So this is going to be t to the 4/3, 3/4, minus 2t, -1 to 1. All right, here, again, what I can do is I can take a 1/3 out. Okay, you can take constants to the outside. You can take constants out. But note that this 1/3 is going to stick around to the answer. All right, so this 1/3 is going to stick around to the answer. So this is x, and again, x2, 1/2. This is x to the 3 over 2, so negative 2/3. 0 to 1, 1/3. So 1 is going to be 1/2 minus 2/3. All right, so t to the 4/3, t to the, what, plus 3, maybe 5/3. So 0 is going to be 0. And then use my super trick here. Teach you that trick in just a second. All right, determine the region of the given region. All right, so determine the area. So that's area under a curve. Notice how this goes from 0 to 1, 0 to 1. So the area under the curve will be the integral from 0 to 1 of our equation, dx. So 1 is going to, again, be 1/2 minus 1/3, 1/6 minus 0. That area is 1/6. Oh, shoot, I should have rounded that. Okay, find the area of this bounded region. So I'm going to kind of cheat a little bit and use my calculator to see what that big graph is. Okay, so it's a curvy, uppy. So this is a curve up, something like this. And we're with 2 as being the minimum. And this is being evaluated from, we have a line. So this is one of our graphs. And the rest are pretty much going to be boundaries. So what is the area bounded by that graph? X is equal to 0. X is equal to 2. And Y is equal to 0. So what is the area bounded by all of those? So that would be, color this area right here. What is that area? So in essence, what this is going to be is this is the integral from 0 to 2 of 5x squared plus 2. So we evaluate that at 2. And evaluate that at 0. That should be our area. Okay, second fundamental theorem of calculus says is this. If I have an upper bound of x, if I have an upper bound of x, all right, and whatever number, I don't even care what number down there. Okay, if I take this with a derivative of x, okay, if I'm taking a derivative of x of this, again, and that is the upper bound, okay, that is the upper bound with some constant in the bottom, all right, what's going to happen is whatever is going on the inside with this, like it could be like t to the third minus 2t plus 4 or something like that. What you're going to do is you're just going to replace this with the letter x. And that's literally what the second fundamental theorem says is this. Is if this is a singular x and you're taking it with a derivative of x, all you do is just replace all the letters with the letter x. So here, they want to know what is the derivative of f. Okay, so they want a derivative of this. So what is the dx? What is the derivative of this? So this is just straight up going to be x squared minus 2x. Again, singular x, derivative of x. This is going to be x to the 4th plus 1 square rooted. Pretty easy. This is the second fundamental theorem of calculus. It gets a little bit more hairy when this upper bound is not a singular x. It'll get weirder when it's like an x squared or a 2x or something like that. And we'll have to do some funny footsteps. But if it's just a derivative of x, easy peasy. And so this is going to be x cosine x. Okay, well, speak of the devil. All right, so ultimately, we are after the derivative of f. Writing that differently, that's df dx. All right? So, and we know that the second fundamental theorem of calculus says if I have like d smiley face and this upper bound is smiley face, if these things match, then any variable that is in here gets replaced by smiley face. All right? So the fancy footwork that is going to occur in this is this. We're going to replace this when we have this obscure upper bound, when it's not what we want, and it's not easily solvable. In essence, what we're going to do is we're going to replace this with a letter U. Right? So you see that I can just simple fractions, these du's in essence are going to cancel out, but we need them to get this done. All right, so this is what I'm saying to you is this. Whatever this upper bound is, if it's not a straight up x, what I'm going to do is I'm going to call that u. So u is in essence, in this case, sine x. Okay, u is sine x. And in essence, I'm also going to need du dx. So the derivative of this with respect to x is going to be cosine x, just a straight up derivative. Not an integral, but a derivative. Okay, so f is now 0u of square root t dt. That's what f is. All right, so back to this, what the hell would be df du? Well, that would be the derivative of f with respect to u. So df du is the derivative of f, which is the derivative of 0 to u t dt. Notice the fancy footwork created a derivative that is the same as that numerator. All right, so that's df du. All right, so putting this all together. This is asking, what is df dx? What is the derivative of f with respect to x? So we begin with df du, which is again d du of integral from 0 to u of square root t dt times du dx, which is cosine x. Okay, so this is going to be the square root of u, just second fundamental theorem of calculus, times cosine x. Now we reverse substitute. U is the same thing as sine x. So this is going to be the square root of sine x times cosine x. It helps my brain out to physically write this, to help me decipher what the heck I'm trying to do. What am I taking a derivative of, and why am I doing it? All right, so again, that upper bound is something weird. All right, so what we're going to do, ultimately, we're trying to figure out what the heck is df dx. So that's going to be df du. I'm going to cancel that du with the dx. All right, so u is x to the third. That means du dx is 3x squared. Okay, so that's that second piece. df du is the same thing as saying d du of f, which is now 0 to u of sine t squared dt. Because again, this is now the letter u because we made that substitution. And so now all we have to do is just put it all together. So df dx is going to be equal to df du, which is again going to be d du of integral 0 to u sine t squared dt times du dx, which is 3x squared. Do the basic substitution. So this is going to be sine u squared times 3x squared. U is x to the third. U is x to the third. So this is x to the third squared. Okay, so that's going to be x to the sixth. How multiply now? So this is sine x to the sixth times 3x squared, which usually goes up